We start the afternoon sections with an invited speaker from Aselsan. He's the manager of the unmanned vehicles, unmanned systems. Yeah. Okay. After this session, we're going to again go to downstairs for the other stations. Then we're going to have the laboratory tour in the Department of Mechatronics Engineering, and then we're going to have the dinner at the restaurant.
Thank you very much. First of all, good afternoon, distinguished guests, dear faculty members, students, and my colleagues. Today, first of all, I want to stress out that I am very honored to be here to share our experiences with you. I am responsible for the Unmanned Systems Department in Aselsan. As the name implies, we work on robots, mostly on ground robots and surface water robots, but even more, we work on motion control of platforms. I will share the details through the presentation. Let me quickly pass through the outline of the presentation. I will talk on the background of the title of the presentation, in fact. And I categorized the major applications in three groups in defense industry. They are stabilized platforms, some mechanisms, automation of mechanisms, mobile robotics. And since it's an important issue for us, I will talk a little bit on stabilization. And at the architecture step, I will describe the building blocks that we use to realize the mechatronic systems. And I will talk on also a little bit infrastructure that we use for developments and some tests we conduct during developments. And mostly, I will go through fielded examples with some video shoots. Yeah, as you remember, the name of the presentation is Mechatronics with Fielded Applications in Defense Industry. You're all familiar with mechatronics. It's a multidisciplinary approach. So, for example, if you need a table, for example, if you go to a carpenter, ask him to design a table, most probably you will end up with a wooden table. And if you go a blacksmith, an iron worker, he will design it with iron. So every specialist tries to approach the problem with its background. But the more wider angle you look to the problem, the more, the higher you have the probability of a smart, good solution. So even today, new disciplines support mechatronics to get smart, really smart solutions. For the fielded application, what I mean, the first word that evokes is experience. The more the system you design and the more the systems are used, you get the deeper experience for the next mechatronic designs. So you consider this experience in your algorithms, in your hardware design, in material selection, even your test design. You would have the chance to include this experience with the used products. And by the defense industry, I mean the harsh environment. Not only it's enough to design the required product or system, you should also consider very cold, hot temperatures, temperature shocks, mechanical shocks, vibrations, and humidity, salt spray, and all combination of harsh environment in the just beginning of the design. Otherwise, you have a low probability of chance to realize a good design. As I said, in the defense industry, we can categorize the products and systems, mechatronic-wise, of course, in three major groups. They are stabilized platforms. Here you see a single weapon platform or an optical platform. The others are some complex mechanisms, and the main task is to realize these mechanisms and automation of these mechanisms. And another area is robotics and robotics motion, of course. What the stabilization is, I take here explanation from the Hill Science Technology Dictionary, is a gimbal-mounted platform usually containing gyros and accelerometers, the purpose of which is to maintain a desired orientation in inertial space independent of the craft motion. Here you see a gimbal system. It includes gyros and some sensors on it, and there is a stabilized object, and with the help of the motors and bearings you try to align it to the target. Even if it's on a sea platform, in a ship, or on a ground platform, your aim is to keep the line of sight of these stabilized object at the target, irrespective of the disturbances caused by the waves, grounds, and motion of the platform. The stabilized object is mostly an antenna, camera, weapon, or a radar in defense industry. So you see a simulation of a stabilization application. Here the tank moves in a curvy manner. So at the above you see the gun moves with the curvy movement of the tank, but just at the below you see the gun is stabilized, and you always aim to just at the center of the target with the help of stabilization. So how we realize these stabilized platforms and other mechatronic platforms? We can represent it with 5 building blocks. Let me make an analogy to understand it better. If you need a robot or a structure, you first have to design the structure or the skeleton of the robot. Then you need to put a brain on it. It's a physical. If we can make an analogy with the brain, like smart controllers. And you need some sensors, eyes or ears. There are gyroscopes, encoders, and some other critical hardware. This can be. So with the outputs you take from the outer world, these are the inputs to the brain, and you evaluate and decide accordingly. You realize these with algorithms in the brain, and you need actuation. You need muscles. These muscles are motors or actuators. And in our company, we try to design each of these building blocks to have the flexibility of getting smart systems. So the more you are good at these sub-building blocks, the more the probability you will get a smart system solution. So we try to design our sub-building blocks. So you see a family of smart drivers. We say it's smart because not only they drive smartly motors, but also they evaluate the sensors from the system. I mean, the gyroscopes or encoders are directly connected to these units with the DSP, digital signal processing board, or CPU board infrastructure. These units evaluate the required signals according to the algorithms run on them, and they accordingly react to the motors to get the units to be stabilized. We use them in air applications, in naval applications, even at the big tank applications. The national tank, Altai, at this application we use the electrical drive units of this family. For the algorithm sub-block, we have many different versions of algorithms. Even I didn't include here. For the robotics, we have different algorithms, but for the stabilized platform, we can categorize them in 2 major groups. They are stabilization control algorithms and automatic target tracking algorithms, which we realize with our own hardware. And we also have designed our motors for these applications. We have a range of brushless DC motors. They are military, of course. We do use in our designs. And for the sensors and actuators, we have packaged and qualified a gyroscope, military gyroscope. We do use mostly these ones in our designs, and we have designed a video tracker board which detect and track the targets in real time. And below it, at the below row, you see some let me say dynamic mechanic units. They are planet gearboxes, rotary and linear actuators, and ring gear. We are also working on the design of these units. By the design, I mean beginning from the subcomponents and analysis, thermal analysis, magnetic analysis, and we end up with the specific unit that we need. For the development infrastructure and tests, we widely use MATLAB and Simulink, and for the simulation, we use steward platforms, different size steward platforms. You see here in the yellow color, and these platforms are mostly 6 degrees of freedom platforms, and they have a band, frequency band about up to 10 Hertz. And we simulate the real life conditions here. So we go put sensors on the real system, for example, a naval ship or a ground vehicle. We take all the disturbance data and we play at laboratory conditions to realize the field disturbances. So we accordingly check and develop our algorithms with the help of these steward platforms. Also, we do widely use motor test setup, let me say, and dynamically we load the motors we designed and with the drivers. So we see the dynamic performance of the motors and drivers, their heat characteristics, their torque speed characteristics, and in every detail before we put the motors and drivers on the system. We conduct tests at this level also. So when we say tests, we have different tests at different levels. We conduct tests board level, unit level. When we integrate the units on the system, we conduct integration tests, and later we conduct environmental tests. Then we go to field and we conduct field tests, and at last acceptance tests with the customers. So at each stage, we test our algorithms, our hardware, according to the specs. But here, what I want to stress out, what I want to accentuate is that we also conduct, it's not a common one, because that's why I want to share, highly accelerated life tests, or highly accelerated stress screen. This is a methodology, in fact, instead of test. We go up to 120, 130 degrees for some units, to see which the first element, what's the first element that fails or recover the failure. Or we go below minus 90, minus 100 degree to see the very cold temperature reaction of the hardware, and accordingly we also conduct very harsh vibration and shock tests on the units, especially on critical units. So here we come to the fielded applications. Here you see a battle tank application. We here realize a modernization project. We put electronics and control infrastructure, and we develop control algorithms for the gun and turret stabilization and for the fire control system. In the tank literature, there's an important issue. There's the hit capability at the first shoot. If you cannot manage to hit the target at the first shoot, you are an open target for the other, for the enemy. So at this project, we mainly increase the first hit capability of the at the first shoot of the tank accordingly. Here you see another application. We work on Altai and Leopard 2A4. Altai is the national tank system, the national tank design of a project. We here design all the electronics, but our group mostly electric drive systems. I mean the motors and drivers and algorithms for the stabilization of the gun. Here you see azimuth disturbance test. If it is not stabilized, the gun moves with the azimuth disturbance. But if it's stabilized, you see that the gun is kept constant, aiming to the target even under disturbance conditions. Here there is another application. It's a missile platform. It's called pedestal-mounted Stinger platform. We realize it for Turkish Army, and also we export it to Netherlands Army. Here you see a test on the platform. There is a elevation disturbance given by the steward platform. The yellow platform is the test platform, and it disturbs the unit. You see the system, algorithm, and the motors react in such a way that they keep the gun fixed to the target in spite of the disturbances caused by the steered platform. Is even in sub-milliradian range that is fixed to the target. This is another application of mechatronics. Here it's a 12.7 millimeter gun system. We call it STAMP in short. It's a stabilized machine gun platform. We conduct field tests. We put this gun on a tracked vehicle. When the vehicle moves, of course there are disturbances, but as you see with the tracked bullets, the bullets are always on the target, irrespective of the movement of the vehicle. In the below case, both the host environment, I mean the ship that we put the machine gun and the target are in move. So we first track the target, and at the proper moment we hit and to the target. This is another application of the stabilization. So there's another one for another machine gun platform. There are many number of platforms, but I only select some of them here. If the time is suffice, I will also show a extra video for this synthetic aperture radar system. It shows all the design stage of this system. Here we mostly focus on the design of an antenna system. We design the structure of the antenna. We put electronics, sensors, and actuator motors on it. It's designed for an air vehicle. We conducted its tests, and it will be integrated on UAV system of day in the next stage. Synthetic aperture radar is used to detect the ground map even in the worst weather conditions. So with the radar principles, it evaluates the signals and detects the moving objects and maps the ground. Now, this is not a stabilized one. We also realized some mechanism designs and automation of these mechanisms. For example, here you see a vehicle. The projectiles are densely stored in the vehicle, so there is no way a human being or a man going inside and carrying the projectile outside. Before it was realized like that, and with a high number of projectiles, these tracked vehicle moves to another vehicle and automatically loads these projectiles to the other vehicles. So to realize this, let me say, mechatronic job, we use 4 different mechanisms. The one turns the projectiles in the small area, makes a circular movement. The other takes the projectile with the help of a hand and horizontally move it. Another mechanism makes increases its elevation, makes the elevation of this projectile and flip the projectile, and another conveyor unit conveys the projectile to the other vehicle. And all of these mechanisms works in 2 directions. I mean, you can make loading or deloading. So perhaps after this short information, I can replay the video. Here we design all the mechanical structure. We design our motors, we design our algorithms, we design our electronics to realize these projectiles. In fact, I say we design, we did use the already enhanced sub-building blocks mostly. This is another example for the mechanism, let me say. It's also a projectile loading system, but here the job is much tougher than the previous one, because we should load 600 projectiles in 1 minute, so the speed is very high, and what's more, we load these projectiles to a gun firing on the move, and this firing regime is not regular, so we should have a mechanical buffer, mechanical accumulator to compensate this irregular regime, let me say. So we designed a accumulator and mechanical buffer. What's more, these guns all the time goes up and down to follow the target. So you should flip these projectiles and change the angle of these projectiles by a flexible body to load synchronously to the gun system. So it's another tough job. So we worked on the design of 4 or 5 different mechanisms to realize the required job. I will show you, after this brief introduction, I will show you a video to see this simulation. Now we are at the prototype test stage of this unit. We realize it. You see the loading of the projectiles, and every time they are loaded, projectiles change, are rotated. So this speed goes up to 600 projectile per unit. So it's a pretty high speed for this type of mechanisms, let me say. You see here the accumulator, I mean the buffer, mechanical buffer, it enlarges and according to the needs to include more projectiles. Here you see the flexible structure that loads the projectiles according to the angle of the gun. Here you see a flexible body. So this mechanism can be considered a complex one. We realized the mechanical design and automation of this system also. Here you see the flexible body, which aligns the projectiles according to the angle of the gun. Last 3 slides are on robotics. In fact, I have many things to share with you, but I summarized what we do in 3 slides. After this one, if the time allows, I will show you another video. Let me say that in the mobile robotics area, what we do, we develop technology building blocks. They are design by wire, drive by wire, and communication, perception, fusion and mapping, navigation and convoy following, coordination and mission planning, unmanned command control centers, autonomy algorithms, payload integration, modeling, simulation and test. In each of these technology building blocks we have algorithms and hardwares, and in the right hand side you see some test platforms. We test these algorithms, these technology building blocks, on these test platforms to verify them and to develop them. By the experience we gained, we realized professional systems, and I will share some of them with you. Here we call this ISG platform. You see here a test. It's an unmanned all-terrain vehicle based on all-terrain vehicle platform. So here in this test, this vehicle carries a balloon system for another weapon system. It's used test purpose because it's unmanned system. We send this robot to carry the balloon for our shoot trials. Here you see this application. And we also integrate a machine gun to this robot, and we conduct remote firing tests of this robot. Also, this is a video shoot for the Kaplan tracked small robots, let me say, ground vehicle. Also, we have demonstrations in USA with some NATO projects. We conduct some common tests with the US with this robot also. Let me say, we do use our own motors, our own servo drivers, electronics inside this tracked vehicle, small tracked vehicle. Perhaps for the 5 minutes I can share you a video with you also. This is synthetic aperture radar. On synthetic aperture radar, you will see the development stage, test stage of the synthetic aperture radar platform, if I manage to play also. Yeah. It will take only 4 minutes, and it will be the last video. It will be the last video. You see different test stage, design stages, the mechanical boxes and all electronics units are designed in CAD system accordingly. And you will see the antenna design stage, synthetic aperture radars antenna, and some CAD design of the antenna to the vehicle, and work on algorithms. Here there are two types of algorithms, of course. One, stabilization algorithms, and other, of course, related to synthetic aperture radar, because the image, the signals taken from this antenna are evaluated to form images, radar images. So you see these stages also. These are the units used inside the vehicle to realize the job. You see also stabilization tests of the antenna system itself. These are the electronics and motors and sensors on the antenna side. It's integrated to the vehicle, air vehicle. For the timing, it's not unmanned, but we will integrate it with some modification to the unmanned system also. The radome section to protect the electronic units and antenna. Now the flight tests of the synthetic aperture radar. I think this is the first image taken by this antenna system. And this is the mission profiles. There are different modes. You will see them in a moment time. In fact, these sections are detailed a little bit are related with the radar. It's strip map mode. While the airplane fly, you have a strip image of the ground, or you can select a region to detect. So the antenna system accordingly stabilizes and looks to the required place. And ground mobile target identification capability. Thank you very much. That's all I want to share with you. Thank you very much for your patience. If you do have any questions, I will try to answer.
What
Yes,
is
please.
the resolution of this synthetic radar?
In fact, I don't know because we were involved in only antenna design section. I know some thing about synthetic aperture radar, but I don't know the resolution figure. Please.
Your unmanned vehicles used operationally in the professional courses?
Yes, for the bomb disposal, we already delivered a few units, and we have some currently ongoing projects for other missions also. But for the time being, we only delivered for the bomb disposal purposes. Okay, thank you very much.
Thank you very much for this nice presentation. Now, we don't have the coffee break, but the other sessions will start immediately. After the sessions, we have the coffee break and another sessions, okay? So, we move immediately once they're done, and we have 2 rooms for the sessions, and we continue immediately.